Have you ever stopped to think about what happens when you get sick? Like, really thought about it? Your
Yeah,
body is basically fighting this microscopic war against all sorts of invaders.
it really is amazing.
And today, we're going all in on one of the most fascinating soldiers in your immune system's army, B lymphocytes, B cells for short.
Right.
These little guys are absolutely critical for keeping you healthy. And by the end of this deep dive, you'll know exactly why.
It's a wild ride, that's for sure. I mean, think about it. We're going to uncover the entire life cycle of a B cell, from where they're born to how they're trained to fight off infections to
Yeah.
all the different ways they keep you safe. I mean, we've got this awesome explanation here that really breaks it all down.
And I have to say, it is pretty incredible. And the
Absolutely.
best part is, by the time we're done, you'll have a much deeper understanding of how this crucial part of your immune system actually works. You'll see how incredibly complex and effective these tiny little defenders really are.
I think that's what's so cool about immunology. Like,
Yeah.
we walk around all day, and this stuff is just happening inside us all the time.
Totally. Okay, so let's start at the very beginning. Where do B cells even come from? Like, where are they born?
Well, every B cell starts its journey in the bone marrow. You can think of it as the birthplace and training ground for all your immune system cells.
Makes sense.
They come from hematopoietic stem cells, which are these amazing cells that can develop into all sorts of different blood cells.
Sort of like the stem cells everyone's always talking about.
Right, exactly.
Okay, so the bone marrow is like this, like a B cell factory, pumping out all these little defenders.
It is. It's really quite something. But it's not just a factory. It's a school, too. As B cells develop, they go through these key maturation stages, all right there in the bone marrow.
Oh, interesting. So what do those stages look like?
Well, the very first stage is the pro-B cell stage.
Pro B.
And then they move on to the pre-B cell stage. And this is where things get really interesting, because this is when they start to create their very first antibody receptor, what we call the pre-BCR.
So the pre-BCR, that's like their first weapon.
You got it. It's like it's their very first attempt at building this incredible threat detection system that's going to be unique to them.
That's super cool.
It is. Okay, and then they develop into immature B cells, which is a huge step because now they have the full B cell receptor, the BCR, on their surface.
Okay, the full BCR.
Right, which is basically an antibody that's embedded in the B cell's membrane.
Got it.
And that BCR acts as their very own personalized threat detector. Like each immature B cell gets its own unique code reader, one that can spot a very specific invader.
So wait, like each B cell is looking for something different.
Exactly. Like one B cell might be looking for, say, the flu virus, while another one is looking for a specific bacteria that could cause, I don't know, pneumonia.
Wow. That's amazing. Okay, so you've got all these B cells developing, each with their own unique BCR. But how do you make sure that those BCRs are actually targeting the right things? Like, how do you make sure they're not attacking your own body?
Well, that is a very important question. And thankfully, the bone marrow has a super strict quality control system. It really is. It puts all those immature B cells through all sorts of rigorous tests to make sure their BCRs are, one, actually working, and two, that they don't bind to any of the body's own molecules. We call those self-reactive.
The health reactive.
Yeah.
Okay.
And if a B cell's receptor does react to something that's, that's part of the body, well, it's either eliminated or deactivated.
Makes sense. Can't have friendly fire.
Right, exactly. So only the B cells that pass this incredibly tough exam, the ones with, good BCRs that aren't self-reactive, only those guys, they graduate to become mature, naive B cells.
Okay, so they've graduated boot camp. They're ready for action. Where do they go next?
Well, these mature but still naive B cells, they leave the bone marrow and they travel to the secondary lymphoid organs. Think of places like the spleen or the lymph nodes.
Okay.
And these are like the front lines of your immune system. It's where they're most likely to run into, those foreign invaders.
Okay. So they're out there patrolling, waiting to encounter a threat that matches their specific BCR. But what happens when they actually find it? Like, how does a B cell actually get activated?
It's all about that perfect match. When a B cell's unique BCR bumps into its matching antigen.
So it's literally like a key fitting into a lock.
It is. And remember, each mature, naive B cell has a BCR with a specific shape.
Right.
And that shape allows it to bind to a particular part of a pathogen or a toxin or even an abnormal cell. And this binding event, that's what kicks off the whole activation process.
So the key finds its lock, the B cell finds its bad guy, and now it's ready to fight.
Exactly. But there are actually two main ways a B cell can get activated. It's not just one thing.
Oh, really? Really? So what are the two ways?
Well, there's T-dependent activation and T-independent activation.
T-dependent and T-independent. Got it.
And the T-dependent pathway, that was more common. And it usually leads to a stronger, longer-lasting immune response.
So what happens in that case?
Okay, so after the B cell encounters its antigen, the one that fits its receptor, it binds to it, it pulls it inside, chops it up in little pieces.
It chops it up?
It does. And then it displays those little pieces on its surface using these things called MHC2 molecules.
MHC2, okay.
You could almost think of it like the B cells putting up a wanted poster. You're showing off pieces of the bad guy so other cells can recognize it too.
That's a great analogy.
Right. And this is where the buddy system comes into play. You see, the B cell needs help from another type of immune cell, a helper T cell, specifically a CD4 plus T cell.
So the B cell is like, hey, buddy, check this out.
Exactly. And if the helper T cell recognizes the antigen fragment that the B cell is presenting, and if it also gets some other signals that it needs.
It needs other signals too.
It does. Then it'll bind to the B cell. And this binding, it's like a handshake between two molecules. There's CD40 on the B cell and CD40L on the T cell. And then, get this, the helper T cell starts releasing these signaling molecules called cytokines.
Cytokines?
And these cytokines are like instructions for the B cell, like, hey, we've got a problem here, let's get to work.
I love how all this is happening at like a microscopic level.
Isn't it amazing?
Totally. Okay, so that's the T-dependent pathway, super coordinated, but you said there was another way.
Right, T-independent activation. This one's a bit different. Certain antigens, like ones with these repetitive structures, like the polysaccharides on some bacteria, well, they can actually activate B cells directly without needing any help for the T cells.
Oh, wow. So they can just go rogue.
Sort of. Like these antigens, they can bind to multiple BCRs on the same B cell, which is enough to trigger activation. It's kind of like setting off multiple alarms at the same time.
Got it.
But it's important to remember that this type of response, it might be faster, but it's not as specific. And it doesn't always lead to those long-lived memory cells that we get with the T-dependent pathway.
So it's like a quicker, less precise response.
Exactly.
So whether it's a coordinated T-dependent attack or a solo T-independent mission, what happens next?
Well, once a B cell is activated, two very important things happen.
Okay.
First, the activated B cell undergoes this thing called clonal expansion.
Clonal expansion. Big words.
I know, right? But it's actually pretty simple. It just means that the B cell starts making tons of copies of itself, like thousands of identical copies, all with the exact same BCR, all ready to fight the same target.
So it's like a B cell army.
Exactly. And second, these activated B cells, they come to a fork in the road.
A fork in the road. Okay, I'm intrigued.
Well, they can differentiate into two different types of cells.
Two types. Okay. Lay it on me.
So one path leads to the creation of plasma cells.
Plasma cells.
Yeah, and this transformation, we call it plasmacytosis. And basically, the activated B cell turns into this antibody factory. Like, its whole job now is just to crank out antibodies.
Okay.
Which are also known as immunoglobulins.
Immunoglobulins, got it.
Right. And it pumps them out into the bloodstream and other bodily fluids. And all these antibodies are specifically designed to target the antigen that triggered the B cell's activation in the first place.
Wow. So these plasma cells are like the weapons manufacturers of the immune system.
The perfect analogy. They're cranking out the exact weapons needed to take down the specific enemy.
I love it. So how do these antibodies actually work? Like, what do they do to fight off infection?
They've got a few tricks up their sleeves, actually. One is neutralization, which is basically, when antibodies bind to pathogens or toxins and they physically block them from infecting cells or causing damage.
Okay.
They can also act as opsonins, which means they tag invaders so other immune cells can find them and destroy them.
Like putting a big target on their back.
Exactly.
I love it.
And then there's the complement system, which is this cascade of proteins that can actually blow up pathogens.
Wait, blow them up?
Literally. It's called lysis. So antibodies, they can neutralize, they can tag, and they can blow stuff up. They're like the Swiss Army knives of the immune system.
That is so cool. And we read that there are different classes of antibodies, like IgM, IgG, and some others. What's the deal with all those?
Yes. There are 5 main classes, and they all have slightly different roles and hang out in different parts of the body.
Oh, okay, break it down for me.
So first up, you've got IgM. This is the first antibody that's produced during an immune response. So it's like the first responder, quickly on the scene.
Makes sense.
Then there's IgG, and IgG is the most common antibody in the blood. And it provides long-term immunity against stuff you've already encountered.
Oh,
And then you've got IgA, which is super important for mucosal immunity. It hangs out in places like the lining of your respiratory and digestive tract.
so it protects all the entry points.
Exactly. Then there's IgE, which is mainly involved in allergic reactions and fighting parasites.
Right.
And last but not least, you got IgD. And honestly, we don't fully understand what it does yet.
There's always more to learn.
Always. But we do know that it's found on the surface of B cells, so it's probably involved in B cell activation somehow.
Got it. So lots of different antibodies, all with slightly different jobs. That's super cool. Okay, so we talked about plasma cells, which are the antibody factories. But remember that fork in the road?
I do.
What about the other path?
Ah, yes. The other path leads to the creation of memory B cells.
Memory B cells. And these are the ones
These are the ones that remember past infections. Exactly.
Yeah.
Not all activated B cells become plasma cells. Some of them become these long-lived memory B cells.
Yeah.
And their whole job is to hang around and wait. They can live for years, even decades.
So they're like the veterans of the immune system.
Exactly. They have all the battle plans from previous infections.
And that's why.
That's why you usually don't get the same illness twice. Or if you do, it's usually much milder. Because the second time around, those memory B cells are like, oh, I know you. And they jump into action way faster than the naive B cells did during the first infection.
Yeah, makes so much sense.
It's really quite clever how the body does that.
Yeah.
And another cool thing is their response is way more effective too. They produce antibodies much quicker. And these antibodies, they often have a higher affinity.
Higher affinity.
Which just means they bind to the antigen more strongly. It's like they fine-tune their aim.
Like an elite sniper team.
Exactly.
And isn't this how vaccines work?
You got it. Vaccines, they basically introduce a harmless version of a pathogen, or just parts of it. And that triggers the creation of memory B cells without actually making you sick.
So you get the protection without the misery.
Exactly.
That's brilliant. Now, I know we've covered a lot, but there's one more thing I wanted to touch on. We read that B cells have other roles beyond just making antibodies. Like, they're not just these single-minded antibody factories.
Right. So what else do they do?
Well, one really important role is antigen presentation.
We talked about that a little bit.
I did, yeah. But it's worth emphasizing, because B cells themselves, they can also act as antigen-presenting cells.
Which are?
Which are APCs for short. And remember how B cells internalize and chop up antigens?
Yes.
Well, they then display those little fragments on their surface using MHC-TI molecules.
Right.
And those antigen MHC-TI complexes, they can be recognized by helper T cells. And that can help activate those T cells even more, which just amplifies the whole immune response.
So they're not just fighting, they're coordinating the entire defense strategy.
Absolutely.
And what about regulation? I read that B cells are involved in, like, keeping the immune system in check, making sure it doesn't overreact.
Yes, they are. It's really important. B cells don't just go on the attack. They also help to keep everything balanced. You know, they can actually regulate how strong and how long the immune response lasts.
They do this by interacting with other immune cells, especially T cells, and also by producing cytokines, those signaling molecules we talked about.
Right, right.
And this whole regulation thing, it's crucial for making sure the immune response is strong enough to get the job done, but not so strong that it starts attacking your own body. You know, that's how you get autoimmune diseases.
Wow. So B cells are like the peacekeepers of the immune system.
I like that. Yeah, they're the ones making sure things don't get out of hand.
Okay, so let's recap. We covered a lot of ground here. What are the big takeaways about these amazing B cells?
Well, first off, I think it's important to remember the journey. You know, from their humble beginnings in the bone marrow to becoming these highly specialized defenders that migrate to different parts of your body. It's really amazing.
And don't forget, each B cell is unique.
Right. Each one has its own specific BCR that's designed to recognize a very specific threat.
Like a microscopic fingerprint.
Exactly.
Mm.
And then we talked about plasma cells. These are the workhorses of the immune response, churning out massive amounts of antibodies. You know, those targeted weapons that can neutralize, tag, and even destroy invaders.
And then there are the memory B cells, the veterans that stick around for years, ready to fight another day.
And it's those memory cells that are responsible for long-term immunity, the reason you don't get the same cold twice.
Right.
And then, on top of all that, B cells play these other crucial roles in the immune system. You know, they help activate T cells by presenting antigens. And they help keep the immune system in check, you know, making sure things don't go haywire.
So they're not just fighters, they're strategists, they're peacekeepers.
They do it all.
I mean, it's just amazing to think about all this happening inside of us all the time.
It really is. Next time you feel a cold coming on or you get a cut that heals, take a minute to appreciate these incredible B cells working tirelessly behind the scenes to keep you healthy.
They're the unsung heroes of the immune system.
Absolutely. And who knows what other secrets they hold. What other amazing abilities we might discover in the future.
I can't wait to find out.
Me too.